Get started. My name is Cody. I'm the Executive Director of Friends of Alta. I'd like to thank you all for coming out for the Speaker Series event tonight. The topic tonight is mountain forests and a changing climate. And we're privileged enough to have Dr. William Anderegg, the Director of the Wilkes Center for Climate Science and Policy and Professor in the School of Biological Sciences at the University of Utah. Dr. Anderegg has been recognized by the National Science Foundation's Alan T. Waterman Award, National Science Foundation's Career Award. He's a Packard Foundation Fellow for Science and Engineering and earned his BA in Human Biology and PhD in Biology from Stanford University, among so many more accolades that would take way too much time. So please join me in welcoming Dr. William Anderegg.
Well, thanks so much, Cody. First of all, it's wonderful to be here with you all this evening. Thanks for the invitation to chat science. I always love these sorts of venues. And I like to walk around. Can folks hear me if I'm walking around? Sounds good? Okay. Hopefully folks on Zoom can hear okay as well. So my story tonight actually starts in kind of down a dusty mountain road in mountains not terribly far from here, but also quite similar to here. So I grew up in Southwest Colorado and spent a huge amount of my time hiking, camping, and fishing in the Colorado Rockies. Skiing as well. And Colorado likes to say they have better snow. Having skied extensively in Utah and Colorado, the snow is better. I totally have become a convert of Utah snow. And where this story starts actually is a lot of my time was spent growing up in aspen forests in the mountains. And as I was starting my PhD in science, I came back to some of those same aspen forests, and where once had been really lush, closed canopies, healthy forests, really fantastic for wildlife, for diversity, for flowers. Instead, lots of these landscapes looked like this, like moonscapes where the forests were dead or dying. And this really prompted a whole set of questions. What is going on here? Why is this happening? This is an incredibly visible and visceral change just within my lifetime. And I wanted to know, what's driving this? Could this be related to climate change? And in particular, what does this mean for the future of aspen forests around the West and other forest types around the West? So that really kicked off a lot of the science that I'll share with you today. The kind of a three-part roadmap of where we're headed. First, a general background of what we know about climate change impacts on Earth's forests and some of the key scientific questions. Second, I'll talk about a lot of our work on drought and disturbance in Western forests, particularly fire and insects as well. And then finally, I'll talk about how can we bring a lot of this scientific understanding and tools and data sets to inform decision makers around management and the sort of conservation and benefits that forests bring to us. Of course, the context and driver on this, as we've known for quite a while, is that due to human emissions of greenhouse gases, temperatures are rising across planet Earth. This is the long-term record from NASA. And when we talk about human-caused climate change, we're really talking about sustained warming from the 1960s onward. That's where we start to see enough greenhouse gases accumulate in the atmosphere that it's pushing Earth's climate out of natural drivers more towards human drivers. Now, Earth's forests, these are the San Juan Mountains that I was just talking about in the beginning of my story. This is from Transfer Campground looking up at the southern San Juans. Earth's forests are really poised on a knife edge between two opposing sets of forces with climate change. On one hand, rising CO2 concentrations in the atmosphere can help plants. It lets them do more photosynthesis and lose less water. And that can drive plants potentially to grow more, take up more carbon out of the atmosphere, and thrive. But on the other side of the coin, the stresses of climate change, drought, temperatures, wildfires, and pests and pathogens are some of the biggest ones we worry about. could overwhelm those benefits of CO2 and actually push forests over the edge, to die off in certain regions. What is fascinating about this photo, and you can see this in some of it, is actually there's lots of dead trees in these forests of many different species. So right here in the middle, you can see, over here you can see dead aspens here, and then there's a lot of dead spruces and some firs in the middle. So what we want to understand is, among these two different sets of forces, which one is likely to dominate and where? And what hangs in the balance is incredible amounts of the planet's biodiversity of species that depend on forests, really trillions of dollars that forests provide to humans in things like clean air, clean water, tourism, timber, property values, and actually the speed of climate change itself. So one of the things that forests do currently forests are a pretty substantial carbon sponge. They take up about a quarter of the CO2 that people put up into the air every single year. And that dramatically slows the pace of climate change. Earth's oceans also take up about a quarter, so only about half the CO2 that people emit every year stays in the atmosphere. And so this benefit from the ecosystems and the oceans is an enormous sort of buffer and slowing down of the speed of climate change. So what we want to know is, will forests continue to do that? Or are we going to see these stresses like drought overwhelm and push forests to lose carbon? And that's what this graph kind of walks out, is that the future of Earth's forests is going to affect climate, and right now is quite uncertain. So what this shows you, this graph is sort of a set of simulations of a lot of our cutting edge climate models. And this is over the 21st century. And the vertical axis is the change in carbon on land. So think of this as if more and more carbon is stored on land, it's going up over time. If you're going below zero, it actually means you're losing carbon on land. And that's going to, of course, accelerate climate change. And what you can see is, this looks like a huge spray out of a cannon. There's an immense amount of uncertainty that the red is a high climate change scenario and blue is a low climate change scenario. And the average is this dark line, but the full range of models is where this circle is, that there are some scenarios where forests and Earth's ecosystems get generally greener and store more carbon. And there are unfortunately some scenarios, and there are actually reasons to expect that this probably should be shifted down somewhat, that these models are perhaps, are very likely optimistic. But even in them currently, there are scenarios where Earth's forests and ecosystems lose carbon because of these stresses like fires and pests and drought overwhelm. Unfortunately, as we saw in the opening part of the story in Colorado, and we see, I think, really every summer and basically every mountain pass that you drive in the West, these are no longer hypothetical model simulations. We are seeing the impacts of climate change on our landscapes already. We're seeing it in more severe fires and longer fire seasons and more unprecedented pest outbreaks. So what my research group tries to do is, how can we improve predictions of how individual trees respond to climate using the details of plant physiology? Sometimes a lot of our work kind of resembles being tree doctors or tree coroners. We're trying to understand how trees get stressed and when trees die from climate stress. Then how do we scale that understanding from a tree level up to whole ecosystems and ultimately to continents and the globe? And then the third piece is really, what do we do with that knowledge? Once we have better tools, better data sets and models, what do we do with that to actually inform decision-making, whether it's a conservationist trying to decide where we should protect, a land manager, a property owner, a ski area, the Forest Service? There's a huge amount of potential folks who might want to use this information. So our work really falls into these kind of three general questions: understanding the physiology of plant response, using various tools from satellites to computer models to scale that up to larger and larger scales, And then how can we inform these different decision makers? And I'm going to give you a specific example tonight of what folks are interested in the carbon storage to help slow down climate change. These are called nature-based climate solutions. Okay, so let's jump into some of our work on the stress in the Western US. What we've been interested in for a long time is how can we use this physiology and ecology of forests to really try to model what I think of as the core triple threat to Western US forests: drought, pests, and fire. Pests here primarily being beetles, although there are some others that do matter. So we spent a lot of our time really trying to understand this widespread aspen mortality event called sudden aspen decline. And this shows you what it looks like being on the ground. This is again in Southwest Colorado. And what we found was that actually sudden aspen decline, we have a pretty strong understanding that it's the breakdown of the water transport system, the vascular system inside trees. So trees have this just absolutely incredible and elegant system of getting water up to their leaves. They have to have water in their leaves to do photosynthesis. And that means they inherently lose water when they're trying to do photosynthesis. Now, what trees do is trees pull the water out of the soil through their roots and then through this vascular transport system called the xylem, all the way up to leaves. And in leaves, then the atmosphere is the ultimate pull. It sucks water out of trees, sucks water out of soils, people, rivers. This is the ultimate pump for the water. And that water just flows along, it's pulled along through really surface tension and cohesion. And that works incredibly well. You can see, this is showing you the pressure, so how hard you have to pull to get the water to the next step. And it gets more and more negative as you go higher up. And so they're pulling more and more to get the water up to the top of the leaves. In normal circumstances, this is a beautiful, elegant system. It's far more efficient and far more powerful than humans have ever managed to design and engineer. The military is interested in copying this system for fighter jets to cool the wings because you have so much heat on wings, and it's far more powerful than any vacuum pump we could ever put together. The problem is during stress, what happens is this pull, like a spring getting pulled more and more taut, goes up. The pull gets pulled more and more until eventually these water columns, like a spring being pulled too far, snap. These tiny air bubbles called embolisms shoot in and block the water transport system. You can actually hear this if you put a really sensitive microphone up to a tree on a hot summer day. You can hear little pops and pings as the air bubbles shoot in and block the water transport system. It sounds a little bit like popcorn. It's kind of a strange and eerie sound. Hearing trees get stressed. For a certain amount of this embolism, trees can survive it. And actually, if you don't water your houseplants for a while, this is what happens. They're going to have a huge amount of embolism, and then they're going to wilt and eventually die. And what we found was this is exactly what's happening to trees. It's a process called hydraulic failure, and it's the loss of this water transport system caused by embolism. So we incorporated this set of scientific understanding to really figure out what are the key pieces of this water transport system that tell you which tree species might be most vulnerable to drought and where. And so the next step is we actually built a lot of different statistical models of when and where forests are getting stressed based on this long-term data the Forest Service has collected and from satellite data. So we get this long-term data from roughly 2000 to present that we can look at the stresses and when individual trees died on these monitoring plots. And then we use climate models to look forward into the future to try to track this stress. So I'm going to now zoom out from just aspen forest and sudden aspen decline and show you some maps of the entire US, because then we were able to do this at the entire scale of US forests. This gives you a sense of sort of our historical model, our historical set um, of building these models. Here on the, so I guess I should say the top is wildfire, and that comes from satellites. We have very good satellite data on where fires burn. And then these bottom two, this is drought-driven mortality in the middle and insect-driven tree mortality on the very bottom. The left-hand column is the actual observed data. This comes from the US Forest Service for the bottom two, and again from satellites put up by NASA on top. And on the right hand are our large statistical models to try to model that observed mortality. In general, we do fairly well. I want to point out also Wyoming has a gap in these bottom two, and that's because the Wyoming forest, the Forest Service data from Wyoming has not been released yet. And so we don't actually, it's just a gap in data. It's not that there's been no mortality. There's actually been a lot of insect mortality in Wyoming, which we do capture. We just don't have the observed data for that. Sorry, Wyoming's weird and they're behind. So what you can see is, of course, is that the drought and insect risks are far and away the highest in the Rockies, and that you see fire kind of all throughout the West, but pretty heavily concentrated, of course, in the areas where we've had major fires in California, Yellowstone, Wyoming, that sort of area. For folks who care about the statistics, I guess the summary here is that the wildfire model is incredibly strong, and that's because fire has a really, really strong climate connection. And it's also because we have so much more data from satellites than we do from ground plots. The other thing that's interesting is actually the drought and insect risks really heavily overlap. And that's partially because drought really stresses trees, and that makes it easier for insects to come in, attack, succeed, and kill trees. So there are good reasons for that. So once we had these models, we can actually then start to, in the sort of a hazy crystal ball, look forward into the future under different climate change scenarios. And what I'm showing you here, again, these are the same three climate stresses of fire, really drought, although we're calling it climate-related, climate stress, and insects, of a couple of different regions. And the different colored lines here are a really high emission scenario. So that's where we do nothing to rein in greenhouse gases, down to kind of a low to moderate emission scenario in green. So red means more climate change, green means less climate change. What you can see here is that actually, especially in the high emission scenarios, fires tend to go up in many regions, but really, really rise in the Western US. You do even start to see more fires in some places like the Southeast. Drought stress in particular and drought-driven tree mortality rises dramatically in the southwestern US and to a smaller degree in places like California and the West Coast. And then, at least in these models, we see a huge amount of insect-driven mortality ramp up in California and kind of other parts of the West. To put that on a map, this actually shows you as you go from less climate change on the left to more climate change, how the different mortality patterns ramp up. Fire is the most noticeable. You can see fires really ramp up in the high climate change scenarios. And again, that's tied to the fact that there's just such a strong climate impact in supercharging wildfires. Happy to talk more about wildfires in the questions. There are lots of interesting things as well around forest management and legacies of forest management like fire suppression. And one of the things I like to mention is we actually have really beautiful, clear studies on how much in these long-term fire trends in the West are climate change and how much are management and fire suppression, past logging, and things like that. And what these studies show is that a little over half is climate change and a little under half is really forest management. And so it is definitely both. And we want to try to leverage forest management to reduce the risk where we can, but it's really kind of a combination of the two that's driving these long-term trends. And of course, these maps are just looking at the climate piece. Okay, so now let me jump to the second story to tell you, which is how can we then start to use this information and inform decision makers who want to better manage forests and prepare for these climate stresses? I think this can really help us in understanding forest management priorities. Where should we be thinking about trying to reduce fire risk or reduce drought risk? Obviously, especially things like fire, but also to a certain degree, insects and drought have pretty substantial risks to communities and infrastructure. And so these might be planning efforts and sort of the wildland urban interface. It certainly has huge impacts on insurance and property values. And we've done one study that I won't talk about tonight is we've actually started to look at these impacts on property values when forests die off. And then, of course, there are direct risks to people and structures and more indirect remote risks of wildfire smoke. We've all been breathing more and more wildfire smoke in the West, and that has huge health consequences for our lungs. And then the third category, and it's what I'll talk the most about this evening, is there's a huge amount of interest in using forests as what are called nature-based climate solutions. Just to define that, these are human actions that are really leveraging forests to try to increase the carbon in the forests and slow climate change. So remember, I mentioned Earth's forests currently take up about a quarter of the CO2 that people put up there. The goal of these types of solutions is to ask, can we bump that up a little bit? Can we bump that up to 30% or 33%? So specifically what these are, they tend to be really kind of funded through carbon markets currently. There's a broad set of strategies, but there's about three major big ones. The first is what's called avoided forest conversion, which just means not cutting down trees, stopping deforestation in places where we can stop it. The second is really trying to restore trees. That's reforestation, and probably much less wise would be something called afforestation, which is planting out trees where they weren't before, where they weren't historically. And it's less wise for a number of reasons. Happy to go into that in questions. And then the third big one is called improved forest management. And that really means changing your management to get more carbon in the trees. The most common way people do that is that they extend a timber harvest interval, that if you used to harvest a forest every 20 years and you bump that out to every 40 years, the trees on average are going to grow bigger and it will store more carbon. You've also probably heard of other things like agroforestry, where you grow crops in the shade of trees. That works pretty well in some regions and in some crops. It doesn't tend to work super well in a lot of temperate regions like the US. It's a much more tropical focused strategy. And of course, there's many reasons why these could be useful, particularly all these other biodiversity and habitat benefits. We talked about all the amazing ecosystem goods and services that forests provide us. So this could hopefully increase those. And right now, there's enormous interest from both governments and private companies in using this as part of their climate plans, using this as part of the strategy to get to what's called net zero so that they are not emitting carbon to the atmosphere on net. Now, to do this, it sounds nice, like let's restore forests, let's conserve forests and get more benefits for the atmosphere for slowing climate change out of it. To do it though, to do it well, we actually have to do four key things. First, you have to implement these strategies in areas which actually cool down the climate on net. Now, what I mean by that, it sounds a little complicated, is of course forests store carbon and that cools down the climate. Pulling CO2 out of the atmosphere cools the climate. But they also interact with the atmosphere in other really important ways. And one of the most important is actually the reflectivity and how bright the ecosystems are. Snow is incredibly bright, and a lot of really sandy soils in dry areas are also incredibly bright. We have a lot of these in Utah. If you were to change that to a forest with really, really dark surfaces, so say you go plant a bunch of conifer trees in a desert over really, really bright soils, that change of going from bright soils to dark trees is actually going to heat up the planet, right? It's like blacktop on a hot summer day. Darker surfaces absorb more energy and more heat from the sun. That change in the reflectivity is actually bigger than the benefits of the carbon storage in some places on planet Earth. Very heavily snow cover dominated and very dry, arid, bright soil places. So those are the places where actually planting a whole bunch of new trees is not a good idea from the climate. It might be a good idea from other things on tourism or diversity of the species there, but it actually isn't going to cool the climate. And so we don't want to really encourage that if we're thinking about it as a climate solution. Okay, second thing they have to do, this one's fairly straightforward, but they actually have to cause a change. If you invest some money in this strategy and you get the same thing that was going to happen anyway, you've just wasted your money and you haven't changed it. So they have to lead to more carbon stored than what would have happened otherwise. Third is that the world is pretty complicated, and you have to account for that if you change land management in one area, it might shift just next door. If you protect forests in, say, Utah, and then they get cut down in Colorado next year, you haven't accomplished what you've been hoping to do. And so this shifting of, say, logging or shifting of loss of forests, both sort of within a country and across countries. Let's say you stop a bunch of trees being extracted from the Amazon, but then they're just cut down from Southeast Asia. That undermines the climate goals. And then the last piece is you have to think about the risks, that if we want to store more carbon in forests today, but then those same forests burn down next year or a decade from now, we haven't done a lot for the atmosphere. So these are the four key scientific pieces that we have to do successfully for forests to help us out even more. What my group has done is think a lot about these climate risks and the human system risks. So the climate risks we've been talking about quite a bit tonight. Fire, drought, and pests and pathogens being some of the big ones, but of course, we probably also care about winds, blowdowns, and hurricanes and other disturbances. And then we also, at least in a policy context, have to think about some of the human system risks as well, that you might have illegal logging come in, or you could have changes in the governance. For example, we saw this in Brazil, that if you no longer start enforcing the policies against deforestation, that deforestation shoots way up. And so we have to be able to be aware of and actually account for these risks. So how can we do that with better science? This is one of the things we've been doing, for example, on fire. And this is showing you the 100-year integrated risk. So looking out to a 100-year period, how big are the risks? And the top map of the US is for the sort of end of the 80s and 1990s. And the bottom half is 2000 to 2017. And you can see that these fire risks, consistent with these long-term fire trends, have increased over time and are really quite high in a lot of these mountain forests. So what we want to do is we have to realize that these risks are in many cases increasing in the 21st century. They vary dramatically in space, right? The risks to forests from fire are fundamentally different in Maine than they are in Southern California. We can start to estimate and model these risks, and that's one of the stories I was just telling you. And I think there's just also a huge need for these publicly available maps and data sets and tools to inform decision making. So some of the core questions we've been trying to tackle is, how do climate risks affect our understanding of how much carbon US forests could store? Do different approaches or different tools or different scientific methods end up giving similar answers about the future of carbon storage, or different answers? If they get similar answers, that's really helpful because we have a lot of confidence in basing decisions. If we get different answers, that means there's a lot more uncertainty about what the future might look like. And then how can we really use this information to guide management and improve policy? In this case, we've been thinking a lot about carbon markets and carbon offsets, which I'm happy to go into in questions. So let's talk about actually the first of these, or the first two of these questions, which is, we asked a really simple question in this study of, do we think US forests are going to gain carbon over the 21st century or lose carbon? So another way to put it is, if we fast forward 80 years from today, Do we think there's more carbon in US forests or less? And how does that vary over space? We looked at this in three different major scientific tools. So the upper left are called Earth system models, and these are these large supercomputer models that are trying to model both ecosystems and the atmosphere and oceans. And in these Earth system models, blue colors mean more carbon. We actually see more carbon in almost every place in the US, except for a weird little blob in Texas. I don't know why. I don't know what's going on with Texas, so don't ask. On the bottom left, this is what's called a niche model, and these are widely used in conservation biology to try to track how climate conditions are going to affect species. So this is a very sort of species-driven approach. And what we see there is actually the red colors here are losses of carbon from forests. And there's losses in a lot of places, but particularly kind of this swath in the middle of the East and the Pacific Northwest. And on net, we see a decrease in carbon of 4% over the 21st century, as opposed to a 45% increase in the first method. Now, on the upper right here, this is the best data constrained model we could build based on all those historical data I was telling you about. So that's from these long-term Forest Service plots, satellite data, and how trees grow back after disturbance. And in my view, that actually tells us probably the most realistic picture, which is that you expect some amount of carbon gains in the eastern US, particularly the Northeast, and also the Pacific Northwest. But generally, you can see these red colors of sort of the Rockies through California, we project are expected to lose quite a bit of carbon. And so on net, it comes out to about a 3-4% slight increase. Now, what you can see is this bottom right is the average of these maps. And this hashing are the places where all three methods agree. So think of that as the areas where we think we have more confidence in what the future looks like. Now, just to connect it to this policy piece, we can actually take, say, that really more robust model that I just showed you and overlay all of the forest carbon offset projects in California's cap and trade market. And just ask, do we think these forest offset projects are likely to gain or lose carbon? Here, the gray dots are the projects that are likely to lose carbon over this century. And I want to draw your eye in particular to this right-hand histogram where about 36% of the acres of the area in these projects we think is likely to lose carbon. Now, forest offsets have a small insurance policy, so they do have an ability to kind of buffer and recover from risk, but it's not based on really rigorous scientific data, and it's far too small. Their total insurance policy is about 8% for climate risks, and we're showing that it should be at least 36%, right? It's probably a factor of 4 or more too small. So to kind of come to this, using some of these tools then to inform decision-making, this is really one of the goals of the Wilkes Center for Climate Science and Policy. This has been a really pretty new center launched at the University of Utah. And we have these twin goals of getting cutting edge science into the hands of decision makers and accelerating practical climate solutions. If you want to learn more, please do check out our website. And also I wanted to invite everyone. We have a climate summit every May at the University of Utah at the Eccles Alumni House. So mid-May, we have a 1 to 2 day fantastic gathering of kind of thought leaders and really dynamic speakers across academia, government, nonprofits, and private sector. So please do check it out. And do come down if you're interested. Just to give you an example and a flavor of one of these tools, this is something that we did in partnership with a nonprofit called Carbon Plan, is we took those same risk maps, that I was telling you about. Let's see if this will. And we were able to build out this web tool where you can start to click on the different risks you want to look at: fire, drought, and insects. And then let's see if the next video will work here. Oh, we've done that one. Okay, let's try this. You can then play out in different climate scenarios in different decades how these risks are likely to change. This is showing you a high warming scenario and how the risks ramp up over time. And then finally, to come back to this dusty road here in southwestern Colorado that my story began with, you can then zoom in to specific regions and draw circles around something you're interested in, and then start to look at, here's the next one. Start to look at the actual risk breakdown and amount of stress in our models that we see, or area burned in wildfires that we see in these specific areas. These are all at about a 2-mile resolution, so it doesn't get down to really high spatial resolution, but you can at least start to see specific patches and areas of forest. So this is just a flavor of the types of tools that we've been building, that we've been talking with a bunch of different stakeholders on how we can make these useful and informed decision making. So just to wrap up, we've seen that there are pretty substantial climate risks to forests in the West, fire, drought, and pests and pathogens being the core ones. We can now start to bring some of that science to bear to understand what does the future of these forests look like, and how can we inform our management and decision making using that cutting edge science. And then the bigger picture that I always really want to end with is that a lot of this, particularly in talking about climate impacts on forests, is a bit of a bummer. But I actually personally am far more optimistic about tackling climate change than I have ever been in my entire career. So I want to end this discussion and the talk this evening with kind of the 3 reasons why I actually think there's a lot of reasons for hope and for optimism that we will tackle, and we are tackling, this incredibly important societal challenge. So reason number 1, and I think actually these reasons for optimism don't get talked about often enough. Reason number 1, we've actually made pretty substantial progress. So 2 decades ago, or even a decade ago, we were on track. This left-hand graph is showing you a thermometer. We were on track for above 4 Celsius of warming global. Now, that's a really devastating amount. It's not clear necessarily that civilization is able to persist super well at 4 to 5 Celsius of warming. The good news is, through a whole set of policies that have been acted already in current action, we're actually now on track for about 2.7 degrees of warming. And if we actually carry out some of the policies that are on the books, you can see these other lines in purple, we head down towards about 2.5 degrees of warming. That's great. We still need to largely get below 2 and as close as we can to 1.5 to avoid a lot of these big risks that we're talking about. So there's a lot of good news that we've made pretty substantial progress already. Maybe another way to say this is, when I started in science, we were always on that highest emissions scenario, that highest climate change scenario, and that was really bad news. We are now on kind of a middle range scenario, and our challenge is to try to get down to a low climate change scenario. Second reason I'm optimistic, there have been really major policy advances in the US and Europe and other places, and this is already moving the needle. This is one of the big reasons why we've been able to bend the curve. And then the third reason is a more sort of economic reason, which is that actually the technologies, a lot of the core technologies that we need, particularly wind, solar, and batteries, but also others, potentially things like electrolyzers, the costs of those are falling absurdly rapidly, which means that it's already the cheapest form of electricity in many regions in the world. And this makes this so much more of a solvable problem and brings so many more benefits to communities and to places like the state of Utah. So finally, I just like to throw out a couple of my favorite resources. If you're interested in learning more, these are 2 of my favorite books on the subject. Katharine Hayhoe, I think probably the world's best climate communicator, has an incredible book about climate change that I really recommend. And then a journalist and energy analyst, Hal Harvey and Justin Gillis, have an incredible practical guide of how to get involved to make an impact. These ones in the center are core scientific resources. So if you want to learn more about the science, the National Climate Assessment for the US and the Intergovernmental Panel on Climate Change for the globe are really the gold standard sources. If you're interested in the education side, I really recommend this National Center for Science Education. And for those folks who like podcasts, I really love this Bolts podcast that is sort of a deep dive into energy and climate policy. With that, I want to thank the incredible group of scientists. This is my lab after a week of field work in Southwest Colorado. I have an amazing team that I get to work with, and they're the ones who really do the hard work. I just get to get up and show pretty pictures. And I want to thank my collaborators and the funding sources that make all of this science possible. So thank you. Happy to take questions. Yeah.
Is it more trees, just temporary storage? And because they come off, so aren't they just kind of
it's a good question. In some places, yes, it's just going to be temporary storage. It really, the way I think of it is there's this concept in ecology of the carrying capacity. How much of an organism's population can that landscape sustain? Climate change is, of course, shifting that carrying capacity in areas where there's a lot of fires and drought. That carrying capacity is going down. The question really is, what is that long-term carrying capacity likely to be for 100 to 500 years, and where are we today? And if we're below that carrying capacity, if we can estimate what that is and bump up underneath that carrying capacity, we think that could be pretty durable storage. If we're above that carrying capacity, it's going down. We're just going to lose carbon from these forests. And that's really the scientific question is, can we estimate what that carrying capacity is and then figure out today, are we down here or are we up here? And so that, in many cases, it's probably temporary storage, but there are going to be areas where, and I think the tropics, many tropical forests is a good example of this, where if you reforested a lot of these parts of, say, the Amazon that were cut down, that's probably way below carrying capacity. Still lots of rain, you don't get wildfires. You might be able to store it for hundreds to thousands of years. Those parts of the forest we think have been around for thousands to tens of thousands of years.
And isn't, the changes you show in the US, aren't they relatively small compared to those that are going on in the Amazon?
The human signals are relatively small. Yeah, so we certainly, of course, have quite a bit of forest management, and it's kind of close to a wash whether we're gaining or losing forest area in the U.S. So we're not seeing widespread sort of deforestation like we are seeing in the Amazon. The actual changes in biomass are reasonably substantial. So you can see in these Forest Service data sets that the state of Colorado, the state of California, a number of states actually lost a decent bit of carbon since 2000. So, a lot of those were climate-driven risks. The mountain pine beetle had a huge impact, and fires and droughts have also had a huge impact. So we are seeing carbon changes, but they're not really deforestation-driven, they're more these other disturbances. Yeah.
As fires happen, is there a lot of good thought put into what's being put back into those forests when there's management maybe to account for the change in the carrying capacity and the biome that can make a difference, even if those trees don't tend to be necessarily financially advantageous to the Forest Service? What do you see there?
There's a lot of work going on. And I would say it's somewhat of a question of, do we have the understanding of what's going to grow there sort of robustly for 100 years? And then the financial capacity, can we actually go get those species and those specific populations and genetics and plant them out? We talked to a number of folks in the Forest Service, and they do think a lot about that on public land, and there is frequently replanting. But it's not always necessarily, they have a strong scientific understanding of what species that should be in what populations. So there are some gaps there, both on the financial side or capacity side and on the scientific side. The other thing that's wild, and I hadn't quite realized this, there was a set of really beautiful studies about 5 or 6 years ago, is they've done a lot of following of fires, and you go in and look up what's coming back. How are those forests doing after fire? And across the West, what these studies found is that in basically the wettest 2/3, you do see pretty robust regeneration and trees are coming back, and it looks like some sort of forest is going to recover there. In the driest third, you don't see it. You don't see trees coming back. I see this in Colorado all the time. Huge fires burn Mesa Verde National Park, and nothing is coming back. It's either grass or it's shrubs. And so, in the driest third, and that really probably is climate change, that there's just not enough water for trees to really survive in those regions. It's not clear that planting any sort of or tree species or genotype is gonna work. Just that sort of, it's shifting out of where trees are going to survive after a fire. Yeah.
What factors or data do you think is missing to create more accurate models to predict how the forest will react to climate in the future?
Yeah, that is a great question. It's something that we think a lot about. My top three, it's a very long list, and scientists love telling you about all the things we don't know. My top three, I think, would be how much can CO2 levels kind of buffer the effects of drought? That's still a big unknown. The second would be the pests and pathogens. And the way I tend to think of this is we have pretty good models of fire and relatively good models of drought. And then our models of all the beetles and defoliators and budworms and moths that attack things are really, really either absent or really coarse. And maybe another way to put this is we've seen things like the mountain pine beetle and the spruce beetle devastate Western forests. What's going to be the next beetle that goes into that epidemic? Can we predict what the next beetle is and which trees and regions are likely to be most vulnerable? So that's my second. And then the third kind of comes to this recovery after disturbance. When and where are we going to see recovery of forests? And when and where is it simply going to be a change in ecosystem from a forest to either a shrubland or a meadow, a grassland? So there's a lot of work in all of those, but I think those are some of the biggest pieces we need better data and models. Yeah.
When you put up your last slide, you said the curve of global warming temperatures is bending down in a good way. What do you think the main drivers being up to this point?
Yeah, it's a great question. There's reasonable evidence that last year might have been the peak of global emissions, which we won't know until kind of roughly March of this coming year. If that's true, that's a really, really big deal. Of course, we need to get emissions kind of down to close to zero, or at least close to where forests and oceans can soak up that remaining bit. The biggest drivers for that are phasing down and replacement of coal in a lot of the developed world, and the massive explosion of renewable energy, even in places like China. So it's possible that China peaked emissions last year due to massive growth in renewable energy. So those seem to be the biggest, that we've phased a lot of coal down. Now, in some cases, it's been replaced with gas, which is maybe it's not going to get us near the way there, but it's probably an improvement, especially in power plants. and then this large technological shift in renewables. Yeah.
Where are you getting the information about peak emissions?
Yeah, so there's a really, I should have thrown that on my references slides. There's a fantastic set of energy analysts in the UK called Carbon Brief, and they do analysis of emissions sort of on a month-to-month basis and year-to-year. And they've done a really great set of analyses on emissions in China and then emissions globally. So they're a great source to check out for that. The IEA is the other kind of big source, the International Energy Agency, and that's really helpful in thinking about future projections. But the IEA is a lot slower at catching up on historical emissions. So this is why I'm saying it's not guaranteed that we've peaked emissions, but all of the signs are pretty promising. The folks who look closely at the data give it about a 70% odds that we peaked last year. So not guaranteed. If we did peak in 2023, that is roughly what needs to happen to keep us heading towards a 2 degrees Celsius warming. But we also have to make sure that it continues to drop through the 2020s and sort of at least decrease emissions globally by about 20% over the 2020s. So that's, whether the peak is just sort of a flattening or an actual then decline matters enormously too. And we don't know. That's hard to forecast. Yeah.
This is outside of your area. Go ahead and back it up, but 30% of our forcing of climate change heating is from methane. We're just touching carbon here, which is 7. So it's a huge bit. Is there anything biologically or anything in the natural sphere that we can do to influence that besides changing our diets and having gas wells?
Methane is not my primary area. My sense is it really is all sort of thinking about the emissions side of the piece, that the sinks, there's not as much ability to manipulate as there is for CO2. I think part of that is, in my general understanding, is that the knowledge of methane sinks that are natural is a lot more uncertain, and kind of where those are and how you might be able to accelerate them is, I think, a lot more in its infancy. Yeah.
My question is much smaller in scale in the sense of, in terms of management, we know the forest is part of the interior, which is based upon extraction and economics. But there's also BLM, there's also Park Service, there's these other agencies. Are there policies that we should be looking at now and into the future to better make ourselves able to take advantage of the science that you have and the science that's coming in the future?
Yeah, that's a great question. I guess I would say there's probably a lot we could do in terms of getting a lot more of these tools and data sets into the hands of these agency folks and land managers. We've been talking with the Forest Service quite a bit and thinking about the climate risks to old growth forests, and how, as they're thinking about management of old growth and mature forests in the US, what are the high risk areas and what are the management actions that you could try to reduce that risk? And there's a lot of interest in using that, but actually not a lot of data sets that are sort of easily usable by given forest managers in a given region. So that's one piece. I do think that there's a lot to be said also for the capacity of those agencies, that places like the Forest Service end up having a lot of resources drained away fighting fires rather than managing fires. And this is this sort of proactive management saves a lot of risk and a lot of economic cost and smoke and carbon emissions down the road. And so bumping up not only the technical capacity, but then the actually sort of folks on the ground doing the management. Maybe that's prescribed burns, maybe that's other management actions. That's a key gap as well, is that relative to the scale of the challenge, particularly here in the West, the capacity, in my experience, for most of these agencies is just far, far too small. And so that's, I think, a big policy piece as well, is really increasing the technical and the management capacity is going to be important.
We were talking earlier about carrying capacity of the forest itself to be able to sustain itself.
Yeah.
Is that related at all to the human environment and the capacity to handle people in that area, more recreation area? Mm-hmm. And what impact is there from, unlimited number or not establishing a number of what is sustainable for us to be able to survive? Are we as humans causing an impact on that forest that is measurable, that we should act on or be proactive about?
Yeah. My sense is in most places, those kind of direct impacts aren't big enough to have a huge impact on forest health. I think probably the one exception that comes to mind is ignition of wildfires, and that in areas, especially when fire risk is high, really, really being mindful and educating folks on what they should do to not ignite wildfires is a key piece. It's kind of this weird dynamic that actually the vast majority of fires in the West have people as the ignition source, although that's actually declining over time. Human ignitions are going down. But actually, the vast majority of the area burned comes from lightning ignited fires. And that's because when people light fires, we're often quicker to get them put out. And when lightning lights fires, it's all over and often in more remote areas. And those are the fires that burn bigger and longer. And so we can definitely reduce some amount of the area burned with ignitions. And I do think that's and kind of education on fire sense. And we need to do that. Yeah.
So as I understand the presentation, it seems like you've been focusing on historical data, trying to generate models to get into projections. But the idea of, with this information, getting it in the hands of people that can create some positive action to slow this negative process down. So at what point, because what I'm kind of not hearing is, when do you make recommendations? I mean, I get the idea that models, projections, it's, I won't say it's loosey-goosey, but there's so many variables in there to come up with a model, maybe unlike weather people who have spent a century, between Canada, Europe, United States, designing models that seem to be pretty accurate.
Right.
Here it seems like, we're I won't say we're in our infancy, but it sounds like we're not at the point where you can kind of draw that map, and this is where the hurricane is going to go. Or, by the way, this section of Colorado is not going to have any trees in 2040. So at what point do you kind of say, well, maybe our models can't get that great, and therefore, based on what we know now, what kind of recommendations, given the fact of what you know, and maybe you're not going to know that much more, right, within the next decade, because a lot of things could go sour in the next decade. So at what point, based on what you know, do you make recommendations? And so, and specifically, here we're kind of dealing with this gondola, right? In the Alta region and in the front Wasatch here. So here they're talking about 18 whatever towers and going in and we know what it is. It can't be any different than logging, right? You don't get towers in even with helicopters. You're going to be driving roads. You're going to be cutting trees. So it would be interesting to get your sense of, one, can you make a recommendation for us here? This is kind of a very big issue. And, and be an advocate for whether, given your understanding of how forests react to the environment, which is human as well as nature, beetles, and fires, is this a good thing or not a good thing? Because right now people are looking at, well, it's going to look really ugly, or it's going to interfere with rock climbing. But is there a chance that taking roads and building towers, increasing whatever human activity, is going to be bad for the forest? The next thing you know, we're going to see, maybe driving all these roads, for all these towers, maybe we're going to be bringing beetles in. So I'm just kind of curious as to at what point do you kind of stop doing what you're doing or continue doing what you're doing, but when do you kind of become an element or an advocate for making recommendations?
Yeah, it's a really interesting question. And I think, so maybe to take the first part of the question first, folks are really interested in this forest space of trying to move as close to we can as the weather forecasting approach. Like, let's make a forecast, let's follow up, and so let's see how it did, and continually improve those models. Now, it's actually a lot harder challenge than weather forecasting because the randomness, the sort of random draw of when does a lightning strike a fire and burn down this area, weather forecasting, we understand the physics and they're only doing the next sort of 1 to 2 weeks. Whereas we're trying to go out 100 years, and that randomness is really, really important. So we'll probably never get as good as weather models, unfortunately, but that's okay. Ultimately, climate change is about a risk management problem. How big are the risks, and where and how can we reduce them? And the important thing about risk management, and this is where the sort of insurance analogy comes in really well, is you don't need perfect data. You just need to improve your data and get better information to make better decisions. So we may not be able to say there's a 90% chance of a wildfire in this area, in this decade or this year, but we have a very clear sense of where there are really high fire risks and where there are low fire risks. And that can really guide what management we want to do. Coming to this question of kind of making specific recommendations, I guess what I would say is there are always going to be trade-offs in different options. And what I think science is really good at is giving folks the data and the information of this is what the impacts are likely to be, right? That you're probably going to lose some trees with this set of management actions or putting in, new roads or something like that. But it's ultimately kind of a set of decision making, right? Of sort of values and discussion of what those trade-offs are. That all else equal, I think none of us really want to see trees lost. And then you have to think about the trade-offs. And that's not really a science question. Basically, science can give us the data and the estimate of, if you did a really detailed study, this is how many trees might be lost. This is how you could minimize it or reduce the impacts. So I guess I would say it's a great question. We do try to provide that guidance, but our approach is generally not to wade in and make recommendations that this is a good or a bad idea, because that's more of a policy and political decision. So maybe not the most satisfying answer, but that's been our approach. Yeah.
So having come from California and been through several earthquakes, and then there was yesterday or the day before,
right? Yeah,
which has serious consequences. We've done a lot in terms of seismic retrofitting and things when it's very unpredictable, just right. Like a lot of what we're dealing with climate change. Mm-hmm. Is there anything we can learn from how we've gone from science to effective action in the earthquake area? Are there things that the climate change folks are doing to benefit from what's been done in the seismic or area.
Yes.
Yeah.
Yeah, and absolutely. And I think this comes to thinking about sort of policies and building codes. So you can think about sort of building codes for fire risk, right? What materials are flammable? How much defensible space might you need? Thinking about those sorts of pieces for buildings and kind of how we build and where we build. The second piece that I think there's a lot more that we can do on the forest and climate side is on warning systems, right? That there are earthquake warning systems. Take cover, an earthquake's coming. We've seen time and time again, we need a lot better fire warning systems. We saw this in Hawaii, we see this in California, that really having warning systems, fires incoming, we need to evacuate, or these roads are likely to be closed is really crucial. Same's true for smoke, that we need better smoke warning systems for really sensitive groups. If kids have asthma and are going to be really vulnerable to smoke coming in, can we warn them 1 to 2 days out that there's going to be a lot of smoke hitting the valley? And really improving those sorts of early warning systems should also help reduce lives lost and folks getting sick. So yeah, huge amount. And I think we can draw a lot of inspiration from earthquakes as a great risk management that's entirely stochastic. You don't know when an earthquake generally is coming. So yeah.
Okay, I'm not talking about the Friends of Alta program because I've seen that in action, but all these other things like, oh, this person died, you go to the memorial page, we'll plant a tree for them, and we do this, we plant a tree. Does that make any difference?
Make a difference in terms of like carbon emissions, or
just the keeping forests regenerated, or
yeah, it's a little challenging to answer. I guess I would say is there are plenty of places where strategic tree planting we can do, and it can matter. After fire, where we want to make sure trees recover in this area, or managing, to try to bring trees back on disturbed places, or recovering brownfields, or things like that. It's the scales of climate change are so big. It really is hard for sort of individual one-off tree planting initiatives to have a big impact. Somebody asked me once, and so I was like, I need to go calculate this. How many trees would you need to plant per year to, from a carbon perspective, cancel out the average American's carbon emissions? And it's 500 trees per person per year. Yes, there's not that much space. That's exactly right. So which is a really clear example of we're never going to plant our way out of climate change. We have to reduce emissions. The best case scenario, and actually I have, I think, a slide to show this. The best case scenario, so this green section is all of the natural climate solutions put together. The best case scenario, if we did everything perfectly and deployed forests and trees everywhere we could, is we get about 10% of the climate problem. So it's meaningful, but it's just one arrow in a quiver that we have to use many, many arrows at in tackling climate change. Yeah.
It seems like that example of like planting a single tree or 10 trees would make maybe more sense in like an urban forest environment where it might not have global climate change, but it could have direct change on cooling buildings or homes or neighborhoods or something like that, which
absolutely.
I think in the long run make a difference. And I mean, I'm assuming you don't have a lot to do with your specific studies doesn't you don't study urban forestry and parks. And
we don't. I have a lot of colleagues who do though. So by osmosis, I've been learning a lot. But
those efforts might make more of an impact in that kind of scale.
Yes, absolutely. Cooling, shade, planting trees in parks and public spaces, absolutely.
And then in Alta case, we're not necessarily planting trees here for climate. in my view, it's because we wiped all the trees out in the 1800s from mining. And so we're trying to, because for those of you who aren't familiar with this in Colorado, those trees didn't exist. Let's say the turn of the century, 1900s. So
no, I'm not criticizing that.
Right.
Yeah.
And then in Phoenix, we're talking about some water imagery, dealing with heat. And one of the things we talk about in Phoenix is planting trees downtown, if you can find space. And that's not going to make a bit of difference on the climate, but shade for people, for humans.
But if it cuts down the need for a house to run their air conditioning, you know.
Yeah, it's true. And I mean, the cooling benefits of trees in urban environments, especially in arid climates, are really, really large, right? A colleague of mine is from Florida, and he told me when he arrived in Utah, he realized shade is actually a real thing. Right? Like shade when it's humid is like sort of, it doesn't really matter much, but in an arid environment, shade and of course also the evaporative cooling from trees transpiring really, really does matter. Yeah.
Separating these risk maps from resilience. So say there is some forest is stricken with drought or a fire. I mean, the areas where the drought occurs, I mean, depends on the resilience of the system as well to return back to its original state.
Yes. Yeah.
In your anecdote of southern Colorado, the plains, which is not terrible. I mean, those are still carbon sinks in themselves. So I'm curious if you could maybe elaborate on separating those two.
Yeah, that's a really great point, and it comes to this earlier question on what are some of the big unknowns that we really need to tackle, and the recovery and resilience piece is really hard to get at because it's at such long time scales, and we often don't have really good sort of time series data of this was a fire, and then we have 50 years of recovery or 20 years of recovery. In almost all of the maps I was showing about carbon, we're actually assuming basically perfect recovery. That if you had a forest with this much carbon and it lost half of it, that it's going to be back on that same trajectory to end up with that same amount of carbon at the same age. And that's because we don't have data yet on kind of when and where that resilience might not be perfect. And the speed of that recovery. So we need to understand that. And this also ties into my mentioning about the drier third of Western US forests don't seem to be recovering after fire. And so, yes, that piece of resilience is not yet in a lot of the models, but we'd like to fold that in the
near future. It's one thing to say, oh yes, these areas are risk averse or have a high risk associated with sorts of parameters, but they could very well be highly resilient.
They could be. The main thing to keep in mind, of course, is that the frequency of the disturbances is going up. So even if you do have perfect recovery after a fire, if that's a really fire-prone area and climate change is, say, doubling the fire frequency, even if you recover every time, you're growing into sort of smaller and smaller forests, right? So the sort of frequency of the disturbances does matter and how that's changing.
I mean, I'd imagine that climate change also reduce.
Right. There are a lot of drivers that do reduce resilience. We've done some work at looking at the impacts of multiple droughts in a row and what happens in a second drought after you come through the first drought. And what we find is some forests actually, it's identical, that the second drought has the same impact as the first drought. And so there wasn't any net change in at least the initial impact. It's not fully the resilience. Some forests, particularly a number of the conifer forests, the second drought is actually worse. And so that is a decrease in sort of at least the sensitivity of the system and probably the resilience as well. There are some mechanisms that resilience could go up. And the main one that I tend to think about is just a different species coming in. That if you lose aspen from this area, it's probably pretty sad for a number of reasons, but if ponderosa pine come in, they might be more resilient to drought than the aspen would be. And so that's a way that you could get more resilience after an initial impact. When and where that happens, whether resilience goes up or down or stays the same, is something that we've been really interested in trying to tackle.
Well, that's something that land managers are aware of, right? You know, a conifer forest dying, all of this loss that's just plant birds.
Right. Yeah.
Don't you have Mount St. Helens, which was 1980? So you've got almost 43 years to see, you know, what when there's total devastation.
Right.
What's actually, you know, that, I mean, that's a perfect example of what you're saying is you do have a location. What does that tell you?
Right. Well, and so I guess I should say there, particularly since the start of the satellite record, we do have more and more data. Because when a fire burns, and really the kind of robust satellite record is about the mid 80s, kind of 84, the present. And so, yeah, we now have 40 years of satellite data to say, well, fire burned in 84, we can now track and see where those forests are today. The challenge tends to be that that basically predicting recovery is a lot harder challenge than predicting the initial impact, right? So from a satellite, you can see, well, a fire burned and then things got more and more green, but you don't really know what tree species was that, and is it, you know, sort of a healthy soil microbiome, and how? So I guess, yeah, we do have there. I should say there are these long-term satellite data sets that you can use, and that's where, you know, this information on fire recovery has come from, is from satellite data. There are Forest Service plots that are also helpful, but those really get harmonized in about the year 2000, and in the West, they get revisited every 10 years. And 10 years is a long time. You can have trees die and new trees come in. And so that's an unfortunate, this comes to also the sort of policy piece. If the Forest Service could actually have the resources to go monitor these plots every year or every 5 years, in the East it's every 5, that would be a huge benefit as well for understanding when do things get knocked down and how quickly do they recover. Yeah.
Are we trying to get back to a place where, like, the natural forces, pre-1960s, kind of like you're talking about, are controlling and guiding the forest? Or is this like a permanent thing that we might have to do, or like counteracting what we
Yeah, it's a really tough question. I think it's going to really depend on where you're talking about. I mean, I think, you know, for landscapes that are sort of heavily managed and there are a lot of people in them, it's probably going to be a lot more active process. You know, what are the types of trees we want here? What are the benefits we want from those trees? And what are the risks to those trees? You know, what is the fire risk of this species versus this species? For something like, you know, huge swaths of public lands, in this case, I think it really is just sort of an adaptive management of how can we aim for sort of healthy, resilient forests with the resources we have. And we have to then basically really be strategic and prioritize where we manage, hopefully based on good science, right? That these are the areas where interventions like a prescribed fire could help this large swath of forests. Yeah, excellent question. We'll do back there then. Good.
on sort of the note of like resilience and resistance to climate change, have you been observing any short-term changes in trees or the tree microbiome or rhizosphere or epigenetic patterns that we've been observing that could help the trees survive that could
Yeah, it's a really interesting question. I would say that understanding the rhizosphere and the microbiome is really just kind of at its infancy. And we actually have a new faculty member coming to the University of Utah who studies forest microbiomes and is really excited to look at the impacts of drought and the impacts of heat on these microbiomes. We sort of anecdotally have seen some potential impacts of the microbiome, but I think we're just really starting to have the tools to get at that. So right now we haven't been able to dig too deep yet. Yeah.
What has been the effectiveness of prescribed burns in Utah? And is there anything we can learn from Native Americans who have been somewhat successful?
Yeah, those are both excellent questions. I think there's probably quite a bit to learn from the Native American forest management practices. And I think in a lot of the pine forests in particular, that there's a lot of important knowledge that we really need to be having those conversations and folding into our management strategies. We were actually just looking at this recently. So prescribed fires, usually the main goal is to reduce the fuels to reduce the chances of a big fire. From a kind of basic biology standpoint, that should work pretty well because fire folks always focus on this triangle of sort of ignitions, weather, and fuels. And if you really reduce any of these, you can reduce fire. So reducing fuels should generally help. What's fascinating is it's really hard to quantify the impact because we do so little area of prescribed burning, and then where wildfires start, especially when it's lightning, is completely stochastic. And so in our analysis, at least since the 1990s to present, we couldn't find any areas in Utah that had a prescribed fire that subsequently burned from a wildfire. So it's just a small sample size problem, right? It's kind of small areas here and small areas here, and they don't often overlap. Now, California is an interesting counterexample because there have been so many wildfires in California. So there's a really nice study that found they could see an actual effect of prescribed fire in these conifer forests in the Sierras. And so in that case, they did see kind of a decrease in fire severity and in fire burned area in areas that were previously prescribed fires. So in California, there have been so many fires, they can see that the prescribed fires are actually it's a modest benefit. I mean, it's not a huge benefit, and it tended to disappear after 6 to 10 years, which tells you, unfortunately, that to have that benefit on fuels, at least in those Californian forests, you have to keep doing it every 10 years. So there is some evidence for that. Yeah.
First of all, I'm very high optimism. Thank you. Secondly, when I was looking at the models and the comparative slide where you showed 3 models and then the slide that they seem to overlay, I'm no scientist, but my eye was gone in the middle of the map where the Dakotas are, and there was no data. And I thought, well, there's a lot of prairie out there, a lot of corn and things that are. But on the western edge of South Dakota, on one model, there was a little swath, and I believe that's all lineage specified there. On one model, it was paper, and on another model, the same exact appearance to my eye, swath was more blue.
Yeah. And
I think, okay, that's a disparagement in models. Then I started thinking, like a sociologist, that when, say, an industrial interest or a population influence looks at this map and says, hey, the country doesn't have models. Are people then going to start to populate industrially and civilly those areas and bring with them rather than solutions based on data and models, some of the same models?
Yeah. Well, there's always this challenge of where do we have no data because there aren't really enough trees to kind of measure that. I mean, I guess I would say it's the wonderful thing about satellites is you see everywhere. And so for things like wildfires, we see grassland fires just as clearly as we see forest fires. That's not true for insect outbreaks. We're fully dependent on the Forest Service data there. And there is some sort of forest threshold that has to have, sort of this amount of tree cover before the Forest Service says, yes, we're going to put in these long-term plots. So yeah, it's a great question. I probably don't know enough about the human decision making to comment on that part, but.
Thank you. I just started to think that perhaps when you were making recommendations, it would be if industry, especially going to impose some kind of reforestation areas that not previously held forests, right, that every recommendation saying be careful with the trail.
Yeah, and that comes to what I mentioned earlier too, that scientists are generally a lot more positive about reforesting than afforesting, which is adding forest to new areas. And there's a bunch of reasons that the big ones being those are probably not areas trees are going to survive long term. Two, you actually tend to lose a lot of soil carbon, especially in kind of rich grasslands. And so it's not necessarily clear you'll have a strong carbon benefit. And then three, there are usually pretty big biodiversity impacts that we tend to afforest with things like eucalyptus trees that have massive effects on all the species and the other plants and animals there. So there are a lot of reasons why I think planting out trees in unforested areas generally doesn't make a lot of sense, and there's a lot of risks. Yeah. Yeah, let's do one last one and then.
Excuse me, this is the most optimistic pitch on this subject I've seen for a while. I mean, you're basically saying that looks pretty. You feel that stabilizing at 2.5 degrees below pre-industrial levels, 2.5 degrees above pre-industrial levels looks pretty much. And we're at about what, 1.8 now?
We're at 1.4.
1.4. The problem in there is what you don't know, I mean, at least as far as I know, there's some nonlinear effects, otherwise known as tipping points.
Yeah.
And those are really hard to model.
Yeah, and I guess what I would say is this is really a battle of tenths of a degree. Every tenth of a degree we get down, and to your point about nonlinear effects, the impacts, even just the economic impacts, much less ecosystems or health or anything else, the economic impacts are massively nonlinear. So every tenth of a degree you get down, the less economic impact and the less human suffering and the fewer extinctions that we see. Tipping points are fascinating because we don't know where they might be, and there's probably a lot of hysteresis in them, and so we won't. For some of them, like ice sheet melt, we may not know that we've crossed them for decades to actively cross them. And all of that is to say, I think the risks of tipping points, again, are another reason why every tenth of a degree we get down, the better. 2.5 is so much better than 3, but 2 is so much better than 2.5. I'm personally not optimistic that we'll hit 1.5, but I think if we're really concerted and actually also get lucky on these feedbacks and the climate sensitivity, we could maybe keep it below 2. So that for my kids, that's my biggest hope, is that we are able to do that. Great. Well, thank you all so much.
Thank you so much. That was wonderful. We've got one more event that we're going to do later in the fall. If you want to make sure you don't miss that, we've got our email sign-up list back there. And that way you can keep up on all the latest news and enjoy wonderful presentations like this. So thank you so much, and thank you all for coming.
The next talk is on air pollution.
So,